After looking at the basic algorithms and techniques like the greedy techniques, today we come to an advanced technique called dynamic programming. Dynamic programming is an algorithm design method. It is used when the solution to a problem can be obtained by selecting a solution to some sub-problems. This is a very loose way of putting it, but we will set up all the formal details in the lecture today. Most importantly, the role of this slide is to tell you that dynamic programming techniques are very fundamentally different from greedy algorithmic techniques. Often in the greedy algorithms there is this power of making a greedy choice, which we have seen in earlier lectures, and the greedy choice identifies a single recursive subproblem to solve. Let us look at the shortest path problem as an example. What you see is a layered graph. It has 4 vertices S, A, B and T, and you also see the edge costs. And if one uses the greedy technique to find the length of the shortest path from S to T by being greedy, in the sense that from S we choose the edge of least weight, then from A we choose an edge of the least weight, and from B we choose an edge of the least weight, then we can conclude that the greedy algorithm will output a path of length 8. However, it is quite clear that the length of the shortest path is indeed 9. In this example, the algorithm does output the shortest path, but let us look at the shortest path in a slightly more complicated looking graph. If we are greedy, then the greedy algorithm will choose the path which goes from S to the vertex A, because the edge weight 1 is the shortest among all the edges that go out of S, and from A it chooses the cheapest edge weight, which is 4, and takes it to the vertex D, and D which chooses the shortest edge whose cost is 18, and we conclude that the greedy algorithm outputs a path whose length is of 23 units, as opposed to the shortest path which is from S to C, C to F and F to T, and the cost of this path is indeed 9. Therefore, it is clear that to solve the shortest path problem, a greedy strategy does not work. Let us just look at the dynamic programming approach, and let us also make some observations about the shortest path. The length of the shortest path from S to T is obtained by calculating the shortest paths via the vertices A, B and C respectively, and then picking the shortest path among the 3. In this example, it's quite clear S has 3 neighbors only, which are called A, B and C respectively. Now if we know the shortest path from A to T and the shortest path from B to T and the shortest path from C to T respectively, then adding up the appropriate edge costs from S and then choosing the minimum will very clearly give the shortest path from S to T. Therefore, what we have now observed is that to solve the shortest path problem, we need to solve recursive versions of the shortest path problem from neighboring vertices. Let us just run the example on, let us just look at the formulation of the distance from S to T, or in other words the shortest path from S to T. Clearly, as we just discussed, distance from S to T is minimum over 1 plus the distance from A to T. The 1 comes because of the edge weight from S to A is 1. 2 plus distance from B to T, because the edge weight from S to B is of cost 2, and 5 plus the distance from C to T, the edge weight from S to C being 5. Indeed, if we know the shortest paths from A to T, B to T and C to T respectively, this minimum gives us the shortest path from S to T. Now the distance from A to T, the relevant part of the graph is shown here. The distance from A to T, as you can see, is the minimum of 4 times the distance, 4 plus the distance from D to T, plus the distance from A to T is given by the minimum of 4 plus the distance from D to T and 11 plus the distance from E to T, where D and E are the only neighbors of A. we can similarly now formulate the distance from B to T, the distance from C to T, and distance from S to T can then be used to calculate. So the distance from B to T is again 9 plus the distance from D to T. The distance from B to T is given by the minimum of the three distances via D, via E, and via F respectively. Similarly, the distance from C to T, there is just a single path that goes through F, and this is given as 2 plus the distance from F to T. One can now observe that the distance from S to T will indeed choose the path that goes via C, which is of cost 9, because that is where the minimum is attained. What we have done in the slide so far is to observe that a recursive formulation of the distance function in terms of distances from other vertices to the destination is helpful in computing the shortest path. It is also possible to observe that one can calculate the distances from the recursive formulations which we have just observed. One can observe that the distance from S to D, an intermediate vertex, not necessarily T, is the minimum of the distance from S to A plus the distance from A to T, and similarly the distance from S to B plus the distance from B to D. In other words, we are taking the minimum of the distances via intermediate points A and B respectively. Similarly, the distance from S to E and distance from S to F are also presented. Now that we have seen this example, let us just formally state dynamic programming and its purposes. It is used for solving optimization problems, which are minimization problems or maximization problems. And in all these problems, a set of choices must be made to get an optimum solution. In the examples that we looked at, the appropriate edges must be chosen to find the length of the shortest path from S to T. The choices are the edges that must be taken by a shortest path from S to T. There may be many such paths. For example, in an undirected graph, every path with the least number of edges from S to T is indeed a shortest path, and our goal is to find an optimal solution. In other words, to find the optimal set of choices. When we design a dynamic programming algorithm, the approach that we take is to first understand the structure of the optimal solution and characterize this optimal solution. By characterization, we mean that we identify certain very important properties of solutions which necessitate them to be optimal solutions. That is what we mean by a characterization. After characterizing the structure of an optimal solution, we then recursively go ahead and write a recursive expression for the optimal solution, and then compute the value of the optimum solution in a bottom-up fashion. The last computation is indeed done via a program, but the first two are analytical exercises, and the computation indeed implements the recursion. As an example, we study the assembly line scheduling exercise, which is an introductory exercise in dynamic programming in the standard textbook by Corman, Lyserson and Rivest, and the pictures that you see are taken from the textbook. Assembly line scheduling can be very intuitively visualized. It is a very important problem in the area of manufacturing. The framework is that of an automobile factory. The framework is of an automobile factory which has two assembly lines. Each line has n stations, n processing stations. On the first line, the processing stations are called S11 to S1n, and in the second line, the processing stations are called S21 to S2n respectively. There are n stations. Now corresponding to the stations, each of the stations have a certain processing time. In particular, for the station S1J, that is the jth station on the line 1, the processing time is A1J units of time, and similarly at the station S2J the processing time is A2J units of time. The entry times into the station are E1 and E2 respectively. The entry times into the lines, that is the entry into the first station S11 and the entry into the first station S21 are E1 and E2 respectively, and the exit times from the stations are X1 and X2 respectively. One can assume that in this automobile factory a car chassis enters one of these two assembly lines and then goes through from one station to another and exits with a completed vehicle. Along the way, along the way a car can stay on the same line by going to the next station in the line, and it does not pay any cost in terms of time duration, or it could transfer to the other line with a cost which is Tij units of time. In other words, if a car gets processed at station S11, then it can either go instantaneously to station S12, or in T11 units of time it can go to the station A22. So what is the problem in this whole exercise? The problem in this whole exercise is that a chassis must be routed through this network. It must visit every station. It does not matter in which line it gets processed, but it must get processed at every station and exit in a minimum amount of time. This is for a single chassis. Now, one of the ways of solving the problem is to actually try all the possible ways by which a chassis could go through the assembly lines, and it is very clear that there are 2 power n of them, and computationally spending 2 power n units of time to actually find out which is the most optimal sequence is not an efficient approach. So the implementation of this idea is essentially to have a bit vector, a binary vector, which essentially says if a certain bit, for example in this case at step 3, if the bit is set to 0, then the vehicle goes through station 4, the vehicle goes through station 2 in step 3, and if it is 1, the vehicle goes through station 1 in step 3. The implementation of this brute force algorithm is to keep a bit vector where 0 indicates that the chassis will go through line 2 and 1 indicates that the chassis will go through line 1. And once these are fixed, the time that the chassis spends in the factory can be easily calculated. It is just the length of the path that goes through these stations. The sum of the time durations on the edges will tell us the total time that the vehicle will tell us the total time the chassis spends in the factory before exiting, and then we can choose the bit vector which gives the least solution, and indeed we would have solved the desired problem. However, we would have spent 2 power n units of time. To avoid this inefficiency in terms of the amount of time that has been spent by the algorithm in finding the optimal path, we try and understand the structure of an optimal solution, which is the first step in the design of a dynamic programming algorithm. in this graphic we indeed have highlighted the optimum path in dark color. We will see how the algorithm will indeed find this particular path. To understand the optimal solution, we invent a parameter of interest. Let us look at the station J on the first line, and let us ask, if a shortest path goes through S1J, then do we have some information as to shortest paths to other stations that preceded it, that are computed in that shortest path. To understand the structure of the optimal solution, we ask the following question: if there are if we look at the set of all possible ways from the start to exit via S1J, there are two possibilities for a path that goes via S1J. The previous vertex before the station S1J could have been the station S1J minus 1 and a direct transfer to S1J, or the previous station could have been S2J minus 1, that is the station on the second line, and they transfer over to S1J. We now make the observation that the fastest way through S1J is through S1J minus 1. In other words, if we consider all the paths that go from the start to exit which go through S1J, and among these, if we consider the path which is the fastest, and let us say that such a shortest path or such a fastest path indeed goes through S1J minus 1, then it is also clear that such a path must have taken the fastest way from start through S1J minus 1. The reason is very straightforward. Indeed, if there is a faster way through S1J minus 1, then we could have used it and found a faster path through S1J. This is really the optimal structure, or it is the structure of an optimal solution. The structure of an optimal solution is the fastest way through S1J contains with it an optimal solution to the fastest way through S1J minus 1 or S2J minus 1, whichever is there in the fastest way through S1J. This is referred to as the optimal substructure property. It is this property that is used to write down the recurrence for the length of the shortest path from S to T or the fastest path from S to T. So what we are going to do now, which is the second step in the process of dynamic programming, is to write down the optimal solution in terms of the optimal solutions to sub-problems. Let us introduce some necessary notation. Let us assume that F star is the fastest time to go through the whole factory, and let Fij denote the fastest time to go from the starting point through the station Sij. Therefore, F star is very clear. F star is the minimum of the two terms, which is F1 of n plus x1, that is the time taken to exit from line 1, comma F2 of n plus x2, which is the time taken to exit from line 2. Therefore, this expression tells us that we need to compute F1 of n and F2 of n recursively. Let us start off with the base case. Let us consider F1 of n. Let us consider F1 of 1, that is through station 1 what is the fastest path that goes through station 1 on line 1. It is a time taken to enter line 1 and get processed at the first station. In this case, as you can see, it is 9 units of time, but the generic formula that we can write down is that F1 of n is E1 plus A11. This is the time taken to enter into line 1 and the time taken to be processed at the first station on line 1. Similarly, F2 of 1 is a time taken to enter into line 2 plus the time taken to be processed at station 1 on line 2. The formulae are written there. F1 of 1 is E1 plus A11 and F2 of 1 is E2 plus A21. In general, we can write down a recursive specification of F1j or F2j. They are symmetric. Let us just look at the case for F1j. So the fastest way through Sij has only two possibilities. The two possibilities are: use the fastest way to come to station j minus 1 on line 1, use the fastest way to cross station j minus 1 on line 1, and then be processed at station j on line 1, or use the fastest way to arrive at station j minus 1 on line 2, then transfer to line 1 and then get processed at station j on line 1. Therefore, F1 of j is the minimum of F1 of j minus 1 plus A1 of j, comma F2 of j minus 1 plus the time to transfer out of the j minus 1th station on line 2 to the jth station on line 1, that is T2j minus 1 plus A1j. Observe that this is a recursive specification of F1 of j. The recursive specification of F2 of j is also similar, and this basically tells us the recursive solution of interest for every station on each of the two lines. Having formulated this recursive specification of the time taken to cross station j on line 1 and the time taken to cross station j on line 2, and this we have done for every j between 1 and n, we now wonder what it is to calculate these values from these formulae. And this is the exercise of computing the optimum solution. And one of the ways of solving the optimum solution is to solve this in a top-down fashion. And clearly, if one tries to compute F1 of n and F2 of n in a top-down fashion, at every step we are taking the minimum of two quantities, and it is clear that the running time of this algorithm, which is to evaluate this recurrence in the top-down fashion, will take an exponential time. In other words, it will take 2 power n units of time, which does not seem to be a significant improvement, which is not an improvement at all over the simple algorithm that we started out with, the brute force algorithm. On the other hand, if one uses the bottom-up approach, one can indeed observe that the values of interest F1 of n and F2 of n can be very easily calculated. The main observation that we make is that for j greater than or equal to 2, the value of Fi of j depends only on F1 of j minus 1 and F2 of j minus 1. In other words, the fastest way of crossing station j on either line depends only on the fastest way of crossing station j minus 1 on line 1 and the fastest way of crossing station j minus 1 on line 2, and we compute the values of Fij as described here in increasing order of j. Let us look at the time taken to cross station 1, which we know In this example, we can see that the fastest way of crossing station 1 on line 1 is 9 units of time. On station 2 it is 12 units of, on line 2 the fastest way of crossing station 1 takes 12 units of time. After this, let us look at station 2. The fastest way of crossing station 2 on line 1 is 18 units of time, and the number in parenthesis says which station was the on which line was the previous station. In this case, the fastest way of crossing station 2 on line 1 is via station 1 on line 1 itself, which is an instantaneous transfer to station 2 and then 9 units of processing time. Also, the fastest way of crossing station 2 on line 2 is to actually go through station 1 in line 1 and then transfer to station 2 on line 2 and be processed at station 2 on line 2. Observe that this is 16 units of time as opposed to 12 units of time plus 2 units of time to transfer, as opposed to 12 units of time at station 1 on line 2 and then instantaneously be transferred to station 2 on line 2 and then use 5 units of time, which makes it 23 units of time. Similarly, at station 3 on line 1, observe that the fastest way of crossing station 3 on line 1 goes through station 2 on line 2 and uses 20 units of time, as opposed to crossing station 3 on line 2, which takes 22 units of time. Similarly, crossing station 4 on line 4 takes 24 units of time via station 3 on line 1 itself, and on line 2 it takes 25 units of time via station 3 on line 1, and crossing station 5 takes 32 units of time via station 4 on line 1 and 30 units of time via station 4 on line 2, and then the exit takes 3 and 5 units of time respectively. Therefore, the quickest way of getting from entry to exit is 35 units of time via station 5 on line 1. Having gone through this whole exercise of identifying the optimal substructure and recursively specifying the distance function and observing that it can be computed in a bottom-up fashion, computing the optimal route, that is the sequence of stations through which the shortest path passes through, is left as an exercise. The next example of dynamic programming which we will study is the problem of optimal matrix chain multiplication, which will be done when we meet next. Thank you.